become of the similar dimensions as the junction depth, also the extent of the depletion region, either on the drain side or on the source side. So then we talk about a short channel device. And the typical manifestations of these short channel effects we'll discuss in terms of two phenomena. One is the how the velocity of the carriers in the channel get limited with the due to this short channel effect. Also, how the threshold voltage need to be modified, okay, in order to take care of the short channel effect, so that we can have a correct value of the threshold voltage. And first of all, let us talk about the first phenomena, that means how the drift velocity of the carriers get limited in the channel. For that, I just wish to draw your attention over a typical three-dimensional view of the channel. Okay, so here you see that across the, across the paper, we show the y-axis. Okay, so this side on your left is the source, on your on the right of the channel is the drain. Okay, and x means x goes perpendicularly. That means into the paper that we are seeing here. Okay, and also so that means this is the length of the gate, and this is the width of the gate. It is in the rectangular, in the rectangle, in the top rectangle. Okay, the length is here and w is here. Okay, and the width, or this width actually we show, see on top of this, as we can see on means physically on top of this we'll have the oxide. Okay, and then on top of this we have got the gate. Okay, that is not visible. Okay, anyway, so it is like it is placed one after another, one over another. Okay, so here we show, so longitudinal field. Okay, remember that we'll have a transverse field as well as longitudinal field. The longitudinal field means that the field which extends between source and drain. So as we know, the drain is forward bias with respect to source. Okay, so the direction of the field will be from right to left. Okay, because drain is more positively biased with respect to source. And the longitudinal electric field, we can the magnitude will be expressed in terms of the drain to source voltage divided by the effective voltage. So this is the, let us say, the effective voltage. That means here in the tapered channel, this is the electrical or effective length of the channel. And as with a progressive increase in the VDS, this effective length will get reduced, and so the longitudinal field will increase. Now the result of this increase of the longitudinal field will be that the drift velocity gets limited. Okay, so in fact, magnitude wise also we see that as VDS increases and L effective decreases, so EY magnitude will increase. Okay, but the result is that due to the ever growing collisions amongst the carriers, that means one electron has started here. Okay, say primary electrons, it has started moving towards this side. Okay, so then it will collide with some carriers. Okay, and then its velocity will reduce, and it does not get time to recover and carry on with its journey towards the drain. Okay, and say as soon as it progresses after that, means the carriers are moving in a what you call large speed. But as the collisions will grow, okay, the energy will be increasing. So due to ever growing collisions, their journey will be what you call impeded, you can say, right? So velocity will decrease. So that means for practical values, let us try to remember that as the value of this longitudinal field tends to exceed about say 10 to the power 5 volts per centimeter. So this ballpark figure, all of you please try to remember. That means as soon as the longitudinal field tries to exceeds 10 to the power 5 volts per centimeter, the saturation velocity will be limited to maximum 10 to the power 7 centimeter per second. Okay, okay. With the as we shall see that with the increase of temperature, as the kinetic energy will grow, so even there is a possibility that this velocity can go even lower. That means it can lie somewhere around 10 to the power 6 centimeter per second. But the maximum, the limit is 10 to the power 7 centimeter per second. Now here I have tried to just derive one expression. I'm sure that you have got this expression from your earlier device course. Okay, but just it's my modest attempt, you can say. Just if you look at look into this as a rectangular parallel pipette. Just look into the dimension. This is the channel length. This is the width of the plate, and this is the thickness. Okay, that means as if the is a three-dimensional channel. Now consider the saturation mode drain current. So this saturation mode drain current can be straightforwardly expressed as the product of current density J and the area. Okay, so that means area means, again you can express the J in terms of product of the charge density and the velocity. Okay, this is from our I mean, when you studied about semiconductor device, so these expressions were dealt with. We are not going into details. That means rho means mobile charge per unit volume multiplied by velocity of the carrier, and the area is there also. So if you try to look into these three parameters, okay, area can be written as, see the cross section, that means the carrier is moving through here. So there are sheets of, that means what do you call, momentary sheets of the uh, carriers. Okay, so that means of this rectangular sheet, this is the W and this is the X. Okay, that is it. So W multiplied by X, and this is rho means mobile charge per volume. So as you see, X and X gets cancelled out. Okay, so what remains is that charge per unit area. Again, you can express in terms of this, that means the electronic charge multiplied by our what do you call, the electron concentration as a function of y. Okay, you integrate from 0 to, this is just for the sake of mathematically putting this in place. So 0 to L effective, and then the saturation velocity multiplied by the width. So ultimately what we have got, the saturation current may be expressed in terms of the product of three things. One is the Qy, that means inversion charge per unit area, then the saturation velocity and the width of the device. This is very important. Okay, so we can write the saturation current expression as the product of width of the device, okay, then the saturation velocity and our this is your gate capacitance per unit area multiplied by VD sat. Okay, so that means charge, but gate capacitance per unit area. So overall, this amount, that means the product of COX and VD sat, will account for the inversion charge per unit area. Now, as this is the saturation velocity, so we are putting the, see, the channel voltage will definitely vary from point to point as we move from source to drain. So we are taking the drain end value, that means VD sat, this channel end voltage. Okay, so carrier velocity saturation reduces. Okay, it means that the saturation mode current will also be below the current value that is predicted by the conventional long channel current equation. In fact, it has been found experimentally that current is no longer quadratically related to VGS. Oh, we have written earlier that, in fact, we shall have a detailed derivation of this, but after a few classes. That means current is no longer quadratically related to VGS. That means we wrote earlier ID equal to, if you remember, mu and COX by 2 into VGS minus VT whole square. That exponent 2 will no longer be applicable when we are talking about short channel device. As we shall see that the current will be linearly related to the gate to source voltage. But we have to wait for certain classes in order to derive that. And also it is independent of the channel length. That is also important. That means the device is said to be in saturation when the carrier velocity in the channel approaches about 90% of its limiting value. Okay. Now, again, once more, in the short channel MOSFET, the carrier velocity channel is also a function of the normal or vertical field component. That is, okay, here you can see that you have got the gate plate, then the oxide insulator, and then the channel. So if gate is positively biased with respect to the underlying substrate, that means there is a vertical field. Okay, and you have got the transverse electric field, okay, which is directed from top to bottom, right? And it has also its effect on the velocity. Okay, so this means this EX, we are talking about EX. So Y extends from source to drain, and X means it is going perpendicularly to the plane of the paper that we are reading. Okay, that we are looking into. Okay, so the dimensions I think should be made clear. UI extends UI, that means UI, the direction is from right to left, but the magnitude is that will be UI, its magnitude will be VDS by L effective, and VGS means it is that VGS divided by TOX, okay, over that oxide thickness. So as EX induces scattering of carriers in the surface region, the surface mobility is reduced with respect to the bulk mobility. Dependence of the surface electron mobility. Again, we have got you can say an empirical relation. That means the effective mobility of the electrons can be expressed in terms of this. That means you have got the low field surface electron. So in the low field, the mobility is normally the normal value. So 650 centimeter square per volt second. Okay. কপিল একটা ক্লাস নিচ্ছি এগারোটার সময় ফোন করবো হ্যাঁ okay, so as you can see that this is a low field electron mobility, okay, and mu n0 divided by 1 plus theta multiplied by ux, okay, where theta is again a empirical factor and ex is the transverse field. Now again, it has been shown, we are not going into details how it has come into being. Okay, you need not remember this also, just to make the impression that the actual effective mobility when the device is in operation with the transverse field and the longitudinal field. Okay, so in all possibility there is a restriction on the mobility attained by the carriers. So this is theta multiplied by the ratio of the dielectric constant of oxide and that of the silicon. Okay, and then you have got the difference, the effective channel voltage, that means VGS minus VCY. Okay, so VC, that means the channel voltage is a function of the of the uh, dimension Y. That means as you move from source to drain, okay, it will progressively be lower and lower. Okay, it will be more reverse biased, right? And divided by the oxide thickness. Anyway, to estimate the field related mobility reduction in a simpler way, one can write it as simply this. That means mu n0 divided by 1 plus eta into VGS minus VT. Eta equal to empirical coefficient. Again, let me tell you that I have no means of explaining how this uh, expression has come into being. But overall, we can say that with the short channel device, in all possibility, the mobility of the device will be restricted. That means the velocity will be restricted, drift velocity, and it will lead to a what you call the actual saturation current will be lower than what can be predicted by the theoretical expression. Okay, and how it will be, we shall discuss more about that. Now, a more important thing for short channel device is how the threshold voltage should be modified. Okay, and for that again we'll take recourse to a simplified geometrical interpretation of the overall voltages and the different depletion regions that now assumes importance in the view of in the light of the short channel device. Let me just explain briefly. So this is the typical what you call the simplified geometry of the channel region. This is nothing but the depletion region. We are not showing the channel proper. Okay, channel proper is very what you call narrow in dimension. So we, for the time being, we pay attention more to the depletion region rather than the channel. Channel is very narrow, constricted region. Okay, here we are not showing this. Rather, we are showing the the gate induced bulk depletion region and the other two depletion regions that results due to the reverse biased PN plus junction here. This N plus junction corresponds to the source, and the other PN plus junction, which is having more reverse biasing effect, this N plus region corresponds to the drain isolated region. Please look carefully. What is this? As you can see, it is this shape is a trapezoid. That means trapezium means that trapezium means this line would have been parallel to this line. Okay, but as the depth of the junction depletion region on the source side is smaller compared to that on the drain side, so we'll have a trapezoidal figure rather than a trapezium. That means here these are the two lateral sides and these are the two longitudinal sides. So even this is not really parallel to this. Okay, because xdd, that means the extent of junction depletion region. This junction depletion region is due to the PN plus junction here, where the lightly doped p-type silicon substrate is there and the N plus heavily doped drain is there. But As the reverse biasing of this PN plus junction is more compared to this, so extent of XDD is more compared to XDS. S corresponds to the source, capital D corresponds to the drain, and small d corresponds to the depletion region. Okay. So please note it carefully. And also here we show this is the mask length of the channel. That means from the metallurgical what you call boundary between the source and the substrate, and that between the drain and the substrate. Okay, this point. Okay, and this delta LD and delta LS. This stands for the lateral extent of the these two depletion regions. Although now we have to look into the three depletion regions separately. One is due to the VGS. Okay, that means this is called gate induced depletion region, right? As you have studied earlier, that means as the gate becomes progressively positive with respect to source, what we go through first the depletion phenomena followed by the inversion phenomena, right? So in the depletion phenomena, we showed that a depletion layer will be uncovered slowly, right? Okay, well, all of us, I believe, will remember. So this depletion region will assume this shape. But now, in the short channel effect, when the effective channel length becomes of comparable dimension with respect to junction depth or even the extent of the depletion region, right? So these depletion region earlier, you see, in the older days for the conventional long channel transistor, where L were much uh, longer compared to XJ, that means the junction depth, or even XDD, XDS. That time we would have seen the junction, the bulk induced or gate induced depletion region as simply a rectangle. Okay, simple rectangle, nothing else, because this was most prominent, and we would have neglected the effect of these two lateral junction depletion region. But in the present day, where L is comparable in dimension to XJ or XDD, now we have to pay a minute attention to the shape of the depletion regions and look into the relative importance of junction depletion region on the drain side as well as the source side. So this will no longer be negligible, right? So that means the depletion region due solely due to the VGS can be restricted in this shape, like a trapezoid, and and the effect of this junction depletion region on the left and this on the right will have to be considered over the expression of threshold voltage. Okay, how that let us see. First of all, consider this expression, namely Vt. Okay, the generalized Vt equal to zero bias threshold voltage plus gamma, where gamma is the body bias coefficient or substrate bias coefficient, as all of you remember, and gamma, the expression I believe all of you remember, that is root over 2q into Na into epsilon Si, okay, into 2 phi f divided by Cox. Okay, and this 2 phi f again is the electrostatic Fermi potential of the p-type substrate, and VSB is the source to body voltage. This is the general expression. Now this is valid only for a long channel MOSFET. Okay, channel depletion region for a long channel MOSFET was assumed to be created only by applied gate voltage, only due to VGS. That was in the older days. And depletion regions due to drain body and source body PN plus junction were ignored. Now, gate-induced bulk or channel depletion region was assumed to be rectangular, extending from source to drain. But in the present day short channel transistors, the N plus drain and N plus source diffusion regions in P-type substrate induce considerable amount of depletion charge. Now, you know why we are talking about depletion charge? Because as you have seen that the physical components of threshold voltage, one was the work function difference, the second one was the component that was required to cause the surface bending, pan bending, and the third important point was the one that was required to offset or balance out the depletion area charge. So depletion area charge will now focus here, and that is a part and parcel of this threshold voltage. So if this changes, okay, then this will naturally change. So in one, the QB in the expression of one, I have not written the detailed expression that we discussed, I think, 2 classes back. Okay, so in the expression for one, QB or the depletion charge supported by the gate voltage was overestimated. Why we say we have overestimated this? Because this entire depletion charge is not due to the VGS. Part of this is due to this source substrate depletion junction, and another part of this QB is due to junction depletion. So the actual QB that will have its effect on VT is not solely due to VGS, but part of this is due to this get induced bulk depletion region. Sorry, a part of this is due to this junction depletion region, part of this due to this. So this we have to subtract from the QV. That means the QV expression we have to modify a bit, and having modified it properly, then its effect on the how the VT should be modified, that we'll see. That is very interesting. Just keep in mind that we'll take some simple geometric figures so that the analysis becomes derivable. That we'll do. For the time being, you see this. Next, what we shall do, we shall expand this. We shall blow up one side and bring in the calculation. So far, let us make this comment. That means the threshold voltage in this expression is larger than the actual threshold voltage. The proper correct threshold voltage will have to be calculated by subtracting something from VT. And what is that amount that we are going to subtract? Okay. So the actual threshold voltage of the short channel MOSFET that we shall calculate will consist of, first of all, trying to find out how much of the depletion, how much of the depletion charge, okay, will be accounted for by VGS, and how much has to be subtracted, as this will be accounted for by this junction depletion region and this junction depletion region. Okay. And as shown above, the bulk depletion region is assumed to have an asymmetric trapezoidal shape instead of a perfect rectangular shape, as it was the case in the earlier conventional days, to represent accurately the gate-induced charge. Let me now take you over to a deeper analysis of this side, and this side will be symmetrical. So we'll focus on the drain diffusion edge. Remember that all the dimensions xj is the junction depth. This is where the carriers are lying, okay, electrons. Then this is the junction depletion region, okay, and this is the lateral extent of the depletion region of due to this drain substrate depletion region, okay. What is XDM? XDM is the vertical extent of the depletion region. XDD is the this one, okay, and XJ is the junction depth. Now see, the expression for threshold voltage must be modified as the bulk depletion charge in the short channel device is smaller than what is expected. Okay. So VT0 for the short channel can be written as the total VT0 minus delta VT0. This delta VT0 we have to estimate now. This is a reduction in threshold voltage due to short channel effect. Prior to that, just again recall delta LS and delta LD is the lateral extent of depletion regions associated with source and drain junction region. Then the bulk depletion region charge contained within the trapezoidal region. This bulk depletion means it is solely due to VGS. Okay, that is the actual. This will be taken care of in the final expression of the VT. Okay, actual threshold voltage. This is charge. So charge divided by capacitance will give me voltage. So actual QB0 divided by COX will be included in the expression of threshold voltage. So bulk depletion region charge contained within the trapezoidal region, that means trapezoidal means this one, okay, that is solely due to, see, the charge inside this trapezoid will be accounted for in the expression of VT, but not this or this. Okay, this is due to this junction, this is due to this junction. Whenever we are talking about threshold voltage, you see what is threshold voltage? Informally, threshold voltage is the minimum gate to source voltage that will cause four different things. That will be due to work function difference, then the amount needed to cause the surface band bending, and also the depletion area charge, and the one that is required to counteract the positive sodium ions, okay, in the oxide oxide semiconductor interface. Now this third component, that means the depletion area charge, should be correctly estimated. That's why we are taking the actual trapezoidal view rather than the rectangular view. This rectangular view would have been correct in the older days when you have got L much larger compared to XD, XJ. But nowadays L is comparable to XDD or XJ even, right? So that's why we have to take a proper view. That's why the trapezoidal picture will now be in force. Okay, and we are having a calculation of how much this depletion charge will be. So this is, we can write it as the QB0 is a negative charge, okay, because immobile acceptor ions. So minus 1 minus delta LS plus delta LD by 2L. Why this? Why this term? Let me explain this. You see, from left hand side, you have to subtract out, okay, one triangle. From the right hand side also another triangle. Now, to average, I mean, to take out their contribution, that means contribution of the this junction depletion region on this total QB and contribution of this junction depletion region on this QB. What we are doing, we are making use of 1 minus is, as you remember, delta LS plus delta LD divided by 2L. This factor 2 is there because we are now averaging out the contribution of this junction depletion region and this junction depletion region over the QB0. So QB0 means what? This is solely due to VGS. Okay. So as we can see roughly that as if there is a rectangle and half of the triangle is due to this junction depletion region, the other half is due to VGS. Similarly, here also half of the rectangle is due to, that means this triangle, right angle triangle, is due to contribution of this junction depletion, sorry, this VGS, and the this right angle triangle is due to this junction depletion. So this we have to subtract, and that accounts for 1 minus delta LS plus delta LD by 2L. Okay, I think it's clear.
Sir,
Yes, yes, yes. Yeah.
sir,
Yes, yes. Please speak up. Who is this? Purendu.
Ankit. Hello.
Oh, Ankit. Ankit. Yes, Ankit. Yeah, Ankit. Please.
Yes, sir. Now, what is the electrical length of the channel?
Okay, okay. So electrical. See what you are considering, Ankit, now to calculate the depletion charge. Now we are not considering the effective length of the channel. That means the effective length of the channel is LEFM, right? But now we have concentrated on the depletion area charge because we are not yet considering the current flow. But how much, what should be the correct expression for the threshold voltage? In order to uh, express the correct, sorry, in order to find out the correct expression of the threshold voltage, we now pay attention to the depletion charge sub expression within the VT. Okay, and this depletion charge, you see that to have a truer picture, the channel depletion charge can be split into three parts. One due to the one solely due to VGS, opposite is the dominant one, and part of this, okay, part of this is due to this junction depletion region, and part of this is due to this junction. Now, this PN plus junction and this PN plus junction is not really a contribution of VGS. Okay, that has come into being due to several things. That means when current starts flowing, okay, the less reverse biasing is on the source side, more reverse biasing on the drain side, and so this accounts for XDD being higher than XDS. Okay, but this is due to the current flow and the longitudinal electric field. But we are considering, see, VT is mainly due to the VGS, okay, gate to source voltage. So here, when we try to have a accurate picture of the gate induced bulk depletion region, so this gate induced charge is now need to be differentiated from the charge due to this junction depletion region and this junction depletion. These we are now trying to separate out from the bulk induced or gate induced depletion region, which is solely due to VGS. So that's why what we need to do, we have to subtract out the contribution for this PN plus junction and that of this PN plus junction, right? That's why it accounts for the expression 1 minus delta S plus delta L2 into root of, say, earlier only this was in place, right? Root over 2q epsilon SI acceptor concentration and 2,5. Earlier this was the total, if you remember, this was the total QB0. Okay, now we are modifying this as in this form, right? Now we are separating out the contribution of the two PN plus junction, one due to the substrate and the source, and the other due to the drain and the substrate. And factor
And
2
sir,
in the denominator. Yes, yes.
why are you averaging it out in case if you need to like you don't want to consider those charges which are contributed because of that depletion region.
Yes, yes, yes. Yeah, because as you see, threshold voltage, it will account for what is the minimum VGS value, right? To account for the bulk induced depletion due to VGS, mind you, not due to other factors. You see, this PN plus junction and this PN plus junction and their depletion region will be prominent because of the current flow. Okay. But as we are considering the expression of VT, the threshold voltage, we have to solely consider the contribution of VGS, not the these PN plus junction and these PN plus junction and their depletion region. So BT, within BT, BT accounts for the part of the voltage that will balance out the depletion region charge. This depletion region charge solely due to VGS, but not due to this PN plus and this PN plus, because their contribution will be prominent when you are taking into account the current flow. But
Yes,
threshold
sir.
voltage means, yeah, threshold voltage means what? Without the current flow, when the current has started flowing, what is the contribution on VT solely due to VGS, not due to the VDS, right?
Yes, sir. So for that, you are actually subtracting those delta LD and delta LS, those
Exactly.
charges, right?
Yes, yes. Right,
So
right, right.
why are you averaging it out? You need to subtract the whole charge, which is coming
Yes,
because
no,
of the
yeah, yeah,
delta
I
LD.
understand. Yeah. See, Ankit, one thing is that why this factor 2 is coming, this roughly you can see that if you visualize a rectangle on this side, okay, then half of the triangle is due to VGS, the other half is due to this. Similarly, here also, if you take a rectangle, just draw a rectangle current. You can see now that my hand is that
Okay,
finger is.
okay, sir.
So
I
here,
understand this.
half of this goes out, above this remains. That's why this factor 2 is there. Okay.
Okay, sir.
I think now
Okay.
it will be clear, right? Okay.
Okay, okay,
A
sir.
very simple geometry. Let me tell you, very simple geometry. Okay. Now let
Sir,
me. Yes, yes,
yes, sir. So, sir, I had a doubt. So, means we are
yes.
mentioning
Understand. Ah,
the short channel effect to be something that the L is comparable to XJ, the junction depth. Uh,
yes.
sir, but if we are doing a scaling, then they both reduce by a factor of S, right? Means all the factors would be reducing by S, then the effect would be the same as before, right? Means why is it causing such effect now?
Yeah. That means looking at the geometry of the channel. So here I've got. Uh, yeah, L actually includes delta S and delta LD. Okay. Also, you have to consider. Uh, yeah, you can say. Hmm. Yeah, your question I've understood. So that means why you're saying why the factor L is coming into the denominator. No, that's what. So proportionally, you can say
No, sir.
that.
No, sir. Means my question was means L is also reducing by a factor of S. Uh,
Mhm.
XJ, XD are also reducing by a factor of S.
Oh, yes,
Means
yes,
so.
yes.
So why is this causing an effect now? Means earlier means it's similar factor reduction, right? Means so the shape would be pretty much similar like it was before, right? Means,
Oh, no, no, no. Yeah, let me tell you. Yeah, I understood. Yeah, so that means, no, not that. Yeah, Janushan, one thing, let me make it clear. All the dimensions are you mean to say that all are proportionally reduced with the factor of S, that's scaling factor. Yeah, but still, uh, junction, when you're talking about short channel transistor, it means that although L is reduced by, but not to same extent actually. That you should keep in mind. That means now, yeah, you mean to say that in the earlier days, XDS, whatever was the value, now it will be reduced. Okay. And L also. So that means, again, no need to consider this here. I understand. But the point is, see, the various phenomena, if you consider, say, DIBL, then induced barrier, loading, all this. So it is not that L and these are proportionally reduced by the same amount. I mean, you are progressively reducing L, okay, by S, and XDS, it does not mean that XDS also should be reduced by S, not like that. Some of the things we don't have much control. That means, okay, although the L is reduced, okay, XJ is not reduced by that amount. So these are the technology parameters. That means these are extent of diffusion, how much the junction depth. See, XJ is not necessarily, although we have written probably in a blanket expression that L gets reduced by factor S, XD should be reduced by AS, XJ by race. So that means as whatever was prevailing earlier, that should hold. No, not like that. Actually, the more attention has been laid on reducing L or reducing W, okay, but not on XJ. XJ, I believe, okay, still it has to be maintained because of the particular N plus doping density and all that. So Xn plus may not be to that extent. That's why reduction of L was more prominent compared to that of XDD or XDS or delta LS, delta L. Right. That means with the growing reduction in the dimension, this reduction is more prominent compared to XDD and XG. That you have to keep in mind. Okay. Now here you
Okay.
see, so basically again to make the picture simpler, I have just written it like this. Suppose again to make things simpler, although it is not strictly speaking a trapezium but a trapezoid. So just to make things simpler to you, I understand that delta LD and XDS and XDD will be different. XDD is larger compared to XDS. But one can use the simple geometry to calculate delta LS, delta LD. Where XDS and XDD are the depth of p-n junction depletion region associated with source and drain junction. And XDM is the vertical extent. This we have stated earlier. Now, what is the value, what is the expression of XDS? That means XDS is what? The extent of depletion region on the source side. That we write as, see, although this is, we are writing simply, in a simplified manner, root over 2 epsilon SI by Q1 into phi 0. But actually, this is this. If you consult your device book, you will find that this type of expression was there. You all studied about that. 2 epsilon SI, sum of the acceptor, that means the acceptor concentration and donor concentration plus Q. But in our case, ND is much larger compared to NA. Okay, that means this N plus the the concentration of electrons here in the N plus diffusion is much higher compared to the whole concentration on the lightly doped p-type substrate. So if it is so, then what we have got, these ND and Na plus ND as if they cancel themselves. What remains is 2 epsilon Si by Qna to phi 0. And what is phi 0? On the source side, you see VDS is taken to be 0. Okay. On the drain side, it is VDS. But on the source side, only phi 0 will be there. This is the built-in or contact potential. Okay. The diffusion potential that is given by KT by Q into log n NDNA by NI square. The built-in voltage. But on the drain side, XDD equal to root over 2 epsilon SI by QNA into phi 0 plus VDS. That means the reverse biasing effect of the drain to source voltage is there. Okay. Now you see here, look into this triangle. ABD, this is a rectangular, a right angle triangle. BC is the hypotenuse. AB and AC are there. So BC square equal to AB square plus AC square. What is AB? AB equal to XDM. BC equal to XDD plus XJ. And this other side is AC equal to delta LD plus XG. So if you write like this, what do you get? Simply this. XJ plus delta LD, that is our hypotenuse, equal to XDM square, that means BC plus AC square, right? So if you write it in details, what do you get? See, we need to now find an estimate of what is the delta LS, what is delta LD, right? So delta LS, here probably delta LD will be given like this. It is a quadratic in LD, right? Delta LD. So delta LD, if you solve the quadratic, you get like this. The discriminant is this one, B square minus 4AC. You write like this. Okay. And you see, XDM and XDD are taken to be almost comparable, so they cancel each other, right? So here we are showing something. XDM and XDD, they are comparable, they cancel each other. What remains is this. Okay. And roughly we can write it as XJ into root over 1 plus 2 XDD by XJ minus 1. Similarly, on the source side, you can write it in this fashion. Okay. So finally, then what we can write is this. Delta VT0, mind you, this is delta VT0. That means VSB is taken to be 0. Okay. So, sorry. So that means XDD, we know what is the amount of XDD. What is the expression for XDD? XDD is higher than XDS, right? Because of the presence of VDS. Other things are same. You see 2 epsilon SI QNA. We are taking it to be absolutely symmetrical. So VDS only matters in making XDD higher than XDS. Other than that, you look into XDD and XDS expression, they are same. So now what we write? Delta VT is equal to 1 minus delta LS plus delta LD. That means instead of delta LS and LD, you can write this expression, okay, XJ into this, okay, by, so QBO by CX. COX is the gate capacitance per unit area. In place of QBO, QB0, you write root over 2Q epsilon SI NA into modulus 2 phi f, okay, multiplied by, you just have to type out the expression of delta LD and delta LS. So XJ by 12 multiplied by uh, root over 1 plus this accounts for the drain side, this accounts for the source side. But you see, look into the presence of capital L on the denominator. If for the long channel transistor, capital L was much larger compared to XJ. That means VT0 threshold voltage shift term varies with XJ by L. For MOSFET with short channel length, smaller L delta VT0 is common because capital N and XJ are comparable. But for long channel transistor, the junction depth was much smaller compared to the channel length. Okay, right. That will matter. That means with the downscaling, okay, capital L has come down, but XJ has not come down. Okay, that may be your that may we try to answer your query, Janesh, that the extent by which capital L has come down today with the downscaling, XJ has not come down by that. Right. So for long channel transistor, capital L was much larger compared to XJ, but in the short channel device, capital L and XJ are comparable. We'll now see some typical numerical expression to make it more clear. Okay. See, we are having an N-channel transistor with substrate doping density, except 10 to the power 16. Then polysilicon gate, that is as a N-type gate, so donor is 2 to the power. This is much higher. Probably we have seen this problem. Just we'll apply this in the context of short channel device. Gate oxide thickness, it is 50 nanometer. Oxide interface fixed charge density is doping density is. Also, the channel is implanted. I'm sorry, have I? Okay, yeah, thank you. So it's there, right? So channel is implanted with the p-type impurities Ni equal to. So as you see, channel is implanted with p-type impurities. Is what is the net effect? As you remember that this is trying to adjust the threshold voltage. So whatever was the earlier threshold voltage, now it will increase. Okay, because assuming that all the p-type impurities will become negatively charged when the operation starts. So that means in order to counteract that, the net positive net threshold voltage will be increased, right? So that we calculate first. As calculated earlier, VT0 equal to 0.4. This was part of the problem that we saw yesterday or on Monday. So now, due to p-type channel implant negatively charged acceptor ions, it will lead to an increase in the VT0. What is that? 0.4 plus QNI divided by COX. Ni is this p-type impurities concentration, that is 2 into 10 to the power 11 divided by COX Q. So you get it to 0.855 volt. That means due to bombarding of the channel with this p-type impurities, the net threshold voltage has increased from 0.4 to 0.855 volt. Okay. Now we pay attention to how much the short channel effect will matter. First of all, you see, plot the variation of VT0 as a function of channel length. Assume the first VDS equal to VSB equal to 0. Second part is that find VTO for L equal to 0.7 micrometer. See, junction depth equal to 1 micrometer. Now you see the channel length is even smaller than that. Okay, this is very surprising, no? But this is the case for short channel device. You see, junction depth is as large as 1 micrometer and channel length is even smaller than that, is 0.7. You see? Achha, second part is VT0 will calculate for VDS equal to 5 volt, VSB equal to 0. Let me now take care of the first part. That means plot the variation of VT0 as a function of channel length. That means channel length is decreased over, say, starting from, say, 5 micrometer, 4 micrometer, 1, even sub-micron. So how the threshold voltage will be reduced? I am showing you the plot, but actually how the values will be coming, I have calculated this and I also ask you to calculate that. Just by applying the voltage, just by applying the the expression that we derived just now. That means delta VT is equal to what? 1 by COX. This is the detailed expression for short channel effect. Now barrier or diffusion potential for this phi 0 equal to this. All the values I'm just using from the given data. So the phi 0 is 0.76 volt. For zero drain bias, that means VDS equal to 0, depth of the source drain junction depletion region is here. So for VDS equal to 0, XDS equal to XDD. Okay, absolutely symmetrical. It will be a perfect trapezium. Okay, so then you get this to be 0.314 micrometer. Just put the value. Now, how much change of voltage? For that also, you have to make use of this expression. Okay, so root over this is actually 2q and this expression 2q epsilon si then Na into this. So this for your benefit I have written, this was calculated earlier also. The charge actually 4.82 into 10 to the power minus 8 coulomb per centimeter square. The area charge density, and this is the gate capacitance per unit area 7.03 into 10 to the power minus 8 farad per centimeter square. So put everything is value 1. Why we are writing 1? Because xj, the junction depth is 1 micrometer and the L will vary. So only thing that is vary is the channel length. The other things remain same. So for the short channel device, that means as you progressively reduce L by and by, this VT0 will also be reduced. Okay, why? Because L is the denominator. So this quantity will be larger and larger with the decrease of L, and hence larger and larger amount will be decreased from this fixed value 0.855. So remember 0.855 volt we get from the consideration of the previous conventional long channel device. Okay, but now as L is reduced, okay, progressively, you see the actual threshold voltage will be reduced. How much? Say for L equal to 0.7, how much it will reduce? It will be reduced bang from 0.855 to 0.584. So I have plotted for you. Okay, yes, I am showing. Again, I have plotted for L equal to 1 micrometer, it will be as small as 0.665. For 2, it will be, I have not plotted, but for 3, it will be 0.792. For 4 also, it will be some value. So you can fill up the blanks. Just put the value of L and calculate it. Okay, right? For L equal to 3 micrometer, I got it to be 0.79. For L equal to 2, I have got it to be 0.665. And for L equal to 0.7, I have got it to be 0.584. So right from 0.855, okay, it has become smaller and smaller to this value, the threshold voltage. Get it, all of you? Okay. Now for long channel device, that means L is greater than or equal to 1 micrometer, VT decreases by as much as 50% of its value for channel length. You say how much? How it is 50%? I am seeing only 0.855 and 0.584. It is not really 50%. Yeah, 50% will be able to show when you are taking into consideration the value of VDS. Just look into the second part of the problem. That means calculate VT0 for L equal to 0.7 micrometer and VDS, that means the drain to source voltage equal to 5 volt and VSB equal to 0. Okay, now see. For VDS equal to 5 volt, the drain depletion depth, this will be larger compared to XDS. So XDS equal to 0.863. Earlier XDS and XDD were same. That was 0.314. Okay. So as a result of VDS equal to 5 volt, you see XDD has increased from 0.314 to 0.863. Almost more than double. And as a result of that, now see delta VT0 will be 0.45. So now the short channel VT0 equal to 0.405. So from 0.584, when you are considering the drain to source bias, that is VDS equal to 5 volt, it has got even smaller. From 0.584, it has become 0.405. So earlier the value was 0.855 volt for long channel device. Now now you will be convinced that the VT decreases by as much as 50% of its value, right? So from 0.855 volt, that was the original VT0. Now it has become as small as 0.405. So from 0.855, it has become smaller to 0.40. So now we are convinced that nearly 50% reduction. Okay, is it clear, dear friends? So this is the numerical example that we have taken help of in order to convince that yes, in earlier days, L was say 5 micrometer, XJ was 1 micrometer. L was much larger compared to 1. But now the junction depth, we cannot tamper much. That means know for sure that XJ will remain as same, because otherwise the transistor cannot be formed. Okay, if you reduce it too much, right? So for that, XJ will remain the same, but L is progressively reduced. For that, actual for short channel effect, the VT has to be, in order to make the correction, something has to be subtracted from the original threshold voltage. Correspondingly, now we show the narrow channel effect. See, short channel effect means the capital L was comparable to XDD, the depletion region. But now, when we talk about narrow channel effect, it means the W, the other dimension, will be comparable. So MOSFET whose channel width W is on the same order of magnitude as the maximum depletion region thickness XDM, it is called a narrow channel device. And what is the significant narrow channel effect? It is that it is the opposing effect. That means the actual threshold voltage of a narrow channel device is larger than that given by this. That is very peculiar. You see, I have drawn again a cross-sectional view of the channel across a narrow channel. But now, see, this is the dimension W. This is the L. This is the drain. We are on the source side. So you see that what is the effect? The physical reason for the narrow channel device, threshold voltage has to be corrected by increasing something. Whereas for the short channel device, we have just seen that threshold voltage has to be corrected by reducing something, by subtracting something. So it is the opposing effect. Why is it so? The physical reason we are just mentioning. Oxide thickness is channel. You see, there is a field oxide. Okay. And this is the the thin oxide. This is a thicker field oxide, which surrounds the channel. Okay. So oxide thickness in channel is T oxide. T-ox, this one. Okay. This is the T-ox. Now, regions around the channel are covered by a thick field oxide. Gate electrode over FOX. This also overlaps above the channel region. That means the part of the channel lies even below the FOX. So earlier we were seeing that that channel is solely covered over its on the top of the channel oxide we have got thin oxide, but we see no, some part of the channel is also overlaid by FOX, the field oxide. So that means earlier we were neglecting this. So some part of the charge QNC we write, NC stands for narrow channel. Okay, QNC, narrow channel. While regions around channel are covered by a thick field oxide, gate electrode over FOX and a part of the channel extends below FOX. FOX means field oxide, thick field oxide. So due to the drain substrate reverse bias, a shallow depletion region forms below the FOX. Okay, and this depletion region just has to be accounted for by VT. That's why VT has to be increased. Earlier, we were not accounting for this QNC. And not only here, this was on all four sides. Okay, so a shallow depletion region forms below the FOX overlap area as well. So gate voltage must support this additional depletion region charge QNC to establish the conducting channel, which is otherwise small with W. So actual threshold voltage for MOSFET due to narrow channel effect is that we have to increase something, right? Yes,
Sir, we have
yes.
another class.
We
Okay,
have
okay, yeah.
another class from
Right.
11.
Just let me just 1 minute. Just add just to give you the underlying phenomena is that due to narrow channel, the value of VT has to be increased by how much? Delta VT0 this. Okay. So this is the delta VT0, and this kappa is the empirical parameter. We don't need how details this has come. Just know it for sure that kappa, the Greek letter, is the empirical parameter XDM by W, and XDM is what? This vertical extent of depletion. That whatever we saw earlier. And for depletion region being modeled as quarter circular disc, you can see we are making the kappa equal to pi by 2. See, pi by 2 into 4 give you 2 pi. So that as if that if you place 4 such quarter circular disc, you got a circle. Okay. So that's why from there probably it has come, but it is empirical, so I don't know details. Okay. Simple formula in one is modified. That means this is modified by adding something. But you can say that due to short channel, this needs to be decreased. Due to narrow channel, this needs to be increased. So there can be some opposing effect. Okay. So for minimum geometry MOSFET with a small channel length and a small channel width, delta VD0 due to short channel and narrow channel may tend to be cancelled out. Okay. But at some point of time, we'll give more prominence to short channel effect. and other for not narrow channel use. Okay, thank you, dear friends. I am stopping. I will not discuss. So next day, on Monday, please attend the class at 10 o'clock. There we shall discuss about the MOSFET capacity. And if any doubt over the material, I'll upload this today on your folder. So if any doubt, please let me know. Okay. Thank you, dear friends. Please stay safe, stay healthy. Okay. See
Thank
you
you,
then
sir.
on Monday. Thank you.